Hi everyone, and welcome back to another AP Calculus video. Today we're going to talk about logistic growth. And so to introduce us to this concept, let's take a look at a typical algebra problem. This might be something you come across in an algebra class when you're exploring exponential growth. And so we have this story. It says almost any algebra textbook will contain a question similar to this one. A culture of bacteria in a petri dish is doubling every hour. If there are 100 bacteria cells to start at time 0, how many bacteria will there be in 12 hours? So we're going to answer the question, right? So we've been taught that when we answer a question like this, we are going to use this equation. So typically we say the new amount, we call it A, equals the beginning amount. We use P for the word principal. And then it's 1 plus or minus the growth rate to the t power. Now, plus is for if we're growing, if the growth rate is negative, or if we're decreasing in the amount, we would subtract that. So the algebra question, sometimes we'll use this equation here, y equals, and we'll use y naught. That always indicates the beginning value. And then 1, we'll say plus or minus r to the t power. So let's go back over here and figure out what things are. The amount that starts, that's my y naught. That's my beginning amount. T equals 0 is my beginning amount. This is going to be t. And if we're doubling, then the growth rate is 100%. So to double, r equals 100%, or numerically 1. We never use a percentage in an equation. So to answer this question, we're going to say y equals 100 times 1 plus 1 to the 12th power. And when we do this, we get, let's see, 409,600 cells. Now, suppose that the textbook editor, seeking to add a little unit conversion here to the problem to satisfy the reviewer, changes 12 hours to 12 days in the second edition of the book. What is the answer to the revised question? Well, if we change it to 12 days, you guys, there's 24 hours in a day, so that's 288 hours. So my new problem looks like this, y equals 100, and then we'll have 2 to the 288th power. Oh my goodness, that's 4.97 times 10 to the 88. Now, let's be realistic. At some point, those bacteria are going to outgrow my petri dish. And at some point, they're going to outgrow the food in the petri dish, the agar that you put in the bottom, that they basically sugar. It's a sugary base. It's their food. They're going to run out of food, and they're going to run out of space. And also, bacteria tend to die at some point. So at what point, based on the limitations of the environment and, the lifespan of the bacteria, at what point would we say, wait a minute, we've had enough. This model no longer represents my situation. So this is not a reasonable answer. No, no, no. So in fact, suppose we have a maximal, fancy word, maximal sustainable population of bacteria in the petri dish is 500,000. How many hours will it take to reach that maximum number? Well, what we're going to do is we're going to solve this equation. 500,000. We want to know at what time, how many hours have passed. And we're going to solve this. We can either solve this graphically by plugging this into y1, this side into y2, and finding the intersection. We can also solve it algebraically. If we divide both sides by 100, we get 5,000 equals 2 to the t using natural logs. We'll get the natural log of 500, or 5,000 equals t times ln2 divided by ln2. You end up getting a value here. T is approximately 12.288 hours. So that makes sense because up here we got 409,000 bacterial cells after about 12 hours. So a little bit longer than that, and we've reached our maximum value. So looking here at number 5, the graph below shows what the graph of the population would look like if it were to remain exponential until hitting 500,000. Let's draw a more reasonable graph and see what it might look like. And hopefully, if you guys are following along, you'll kind of draw this graph. And if 500,000 is our maximum, what we're saying is that the limit of this function, so the limit as t is approaching some sort of infinity, right? So as t approaches an infinite amount of time, the limit of my function y must be 500,000. Well, you guys, we should hopefully remember that the definition of a horizontal asymptote is that you have a limit of a function as the independent variable approaches infinity. So it might look a little something like this. It might kind of go up exponentially at first, but at some point it's going to peter off and approach that value. And it might go above the asymptote. You can cross a horizontal asymptote. The idea is that it'll come back down and it'll hug that line, and you might have more and then they'll die off, but it'll always want to be approaching that line. And so we have a change in concavity right there. We also have an asymptote. So, and this has a name. It's called a logistic growth curve. And a logistic growth curve takes into account factors in the environment that would limit our problem. And anytime we have a logistic growth model like this, we want to be able to explore it, and we want to be able to identify a couple of things from the equation. We want to know, number one, what is the maximum number for the system? Sometimes we call that the carrying capacity. So this limit, this 500,000 bacteria cells, is the maximal sustainable population. It's called the carrying capacity, and it's dependent on environmental factors. We also might want to talk about, when my rate is growing the fastest. We might want to ask a lot of questions about this. And so that's what this lesson is about. We're going to explore these situations, in an effort to kind of analyze and learn some things happening. So, exponential growth is only good for a short period of time. At some point, the growth model changes and becomes what we call this thing called a logistic growth model. And so here we have it, where exponential growth follows this format, dy dt equals k times y, so you're doubling, right? So that was our initial problem where we had our bacteria doubling. So the rate of growth, we would say dp dt, the population of the bacteria was 2 times y. So we would double each, as time was changing, that y value was doubling. Here we have a similar situation. It's still k, it's still a constant times that population, and I should be consistent over here. It was 2p. There we go. So over here we still have that exponential growth, but now we multiply it by this thing called the limiting factor. And we have these two variables. P is the population. That's my variable. M is this thing that we're going to call the carrying capacity. And so this is my model. This is a logistic growth model. And when I look at the equation, I should be able to pull two numbers out. M being my carrying capacity, and then K, which is part of my growth constant. That's going to be part of my growth rate. It's, am I doubling, am I tripling, that sort of a thing. So let's take a look at another example here. So consider we have this positive population P that satisfies dp dt equals blah, blah, blah. It's our logistic growth equation. M and K are going to be positive constants. Our first question says, for what values of P will the growth rate dp dt be close to 0? Well, we're going to be 0. Remember, this is factored form. We're going to be 0 when either P is 0, so when the population is 0, or when M minus P equals 0. Well, when M minus P gets close to 0, in order for that to happen, M has to be approximately the same as P. So when M and P are, when the population, the actual population approaches the carrying capacity, the growth rate goes to 0. That should make sense, right? As I max out the room and the food, my growth rate slows down and becomes 0. So when the population approaches carrying capacity, or the max, dp dt approaches 0. Okay, so that's kind of what I'm getting at here. So question 2 says, as a function of P, y equals blah, 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 has a graph that is an upside down parabola. Oh. So when you graph this, it's a parabola. It's an upside down, upside down parabola. So it looks a little bit like this. When I graph it, I'm going to have x-intercepts here when p equals 0. And I'm going to have an x-intercept here when p equals m. So this is the equation y equals, and you know it's a parabola because it looks like this, y equals kpm minus kp squared. So it's an upside down parabola. So remember, p is like your x. So it's a parabola. So the differential equation, the derivative, is a parabola. Okay, so with this in mind, I want to know what is the value of p at the vertex of this parabola. Well, if we know anything about parabolas, we know that it is symmetric. So if we cut it in half, when p is 0, okay, we're having an x-intercept. When p is m, we have an x-intercept. That's when the y value, or dp dt, is 0. So halfway between 0 and m would be m over 2. So right here, this is m over 2. So this is the vertex. The vertex is a maximum. So what we're saying here is that the vertex exists when p equals m over 2, when the population is half of the carrying capacity. Oh, so when we get halfway to our maximum, our growth rate, vertex, in other words, my growth rate is a max. Oh, so the growth rate, the graph of dp dt changes direction. Okay, so we're changing direction at p equals m over 2, right? So let's think about this. We're going up and we're going down, so we know we have a maximum. So because we change direction, we know we're going to have a maximum rate of change. And so using this answer here in part 2, explaining why the growth rate is maximized when the population reaches half of the carrying capacity. Well, if this is the graph of dp dt, which we're calling y, so this is the graph of dp dt, has a max at m over 2. So the growth rate is at a max when p equals m over 2, half of the carrying capacity. Okay, so if the initial population is less than m, is the initial growth rate positive or negative? So let's think about this. Remember, dp dt, if the initial population is less than m, if we have a maximum growth rate right here, that means my growth rate is going down on one side. It's going up, 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 up. It hits that max, and then it's going down. So if the initial population is less than m, is the initial growth rate positive or negative? Well, if we're below m, we have a positive growth rate. So that means that when I look at my logistic growth curve, so again, so this is dp dt, this is p. The population goes up and then levels out. Well, if I hit my carrying capacity m, so as long as I'm below m, I'm growing. If I go above m, then I'm going to come back down, and I might hug it a little bit. So if I'm above m, I'm going to have a negative growth rate. That means I'm going to come down. I need to slow down. So if the initial population is greater than m, what that means is my initial population is up here. It goes down. And it might go down, you know, a little bit. But anytime we're above that m, that carrying capacity, we're going to have a negative growth rate. We're going to decrease our population until we hit that. So we have enough agar for 100,000 bacteria. If we put 200,000 in there, it's going to decrease. It can only support. Makes sense, right? Number 6, if the initial population equals m, what is the initial growth rate? Well, if p sub 0 equals m, then I'm going to have that m minus p. That's going to be 0. dp dt is going to be 0. So if we come in right here at m, right here, we're not going to grow. We're going to just stay put. So if my petri dish can support 500 bacteria and I put 500 in there, then we're done. That's it. Not going to grow. So then number 7 puts all of this that we're talking about into limit notation. It says, what is the limit of p t? Well, the limit of p of t as t approaches infinity, we kind of discussed it back in that first exploration. It's all based on this graph right here. So remember, this is time. As time is approaching infinity, this is p of t. Well, as time approaches infinity, p is approaching that value m. So the limit, as t is approaching infinity of that population, will always be the carrying capacity. So the limit of the population, that's what this is asking for all time. Right? That's kind of how we think about this in English. So the limit as t approaches infinity of p of t, the limit of the population, is always going to be m. It's going to be that carrying. And your AP exam likes to ask you about the carrying capacity using this limit notation. So be on the lookout for that and make sure you jot this down. So now let's take a look at some actual examples. So we've got the growth rate of this population of bears in a newly established wildlife preserve modeled by this differential equation dp dt equals blah, where t is measured in years. What is the carrying capacity for the bears in the preserve? So we're going to remember that dp dt is always kp and then m minus p. So this should be what we have in our notes. dp dt equals kp times m minus p. And if we remember that, and let's move it so that I'm not blocking it off here. So if we remember that that is the case, p dt, then all we have to do is we have to come over here to our equation and we're going to pick out something. So m is always going to be whatever is subtracting p. So I have to make sure, number one, that it meets the criteria, that it looks like my problem. So it does, boom, 100. That's my carrying capacity. So nice and easy, 100. 100 bears. So now I want to know, what is the bear population when the population is growing fastest? So when I am growing the fastest, we talked about how p is half of the carrying capacity. So that's going to be 100 divided by 2. That's going to be 50 bears. So when I have about 50 bears in that preserve, they are multiplying the fastest. They're growing the fastest. They're going to start slowing down though. So now we have this question, and it says, what is the rate of change? Move this. What is the rate of change when it is growing the fastest? Well, we want to know what the rate of change is here. And the rate of change when I'm growing the fastest is simply going to be what I get when I plug 50 bears in. So when p is 50, what is dp dt? That's what this question is asking. What is the rate? So dp dt, and I'm going to get my calculator out, is 0.008. I'm going to put 50 in for p. And I'm going to get 20 per, what is our rate? So let's see, t is measured in year. 20 bears per year. We are growing at a rate of 20 bears per year. When my rate is growing the fastest, that is the maximum that rate will be, 20 bears per year. That's the fastest we'll be growing. Every other rate will be below 20 bears per year. So how do we find the solution? If we know that dp dt equals kp times m minus p, how do we find the solution to the differential equation p of t? How do we solve that? Well, the answer is this. We have to use a lot of integration techniques, including partial fractions. And I'm going to run through that. That's another video. So if you'd like to see this worked out, you can watch the extra bonus video about how this solution comes about, and you can watch it. You're not going to be responsible for it. However, the solution that I want you to write into your notes is simply this. The solution will always look like this. P equals, this is the solution, m, which is your carrying capacity, over 1 plus a times e to the negative mkt, where the m and the k come from dp dt. So remember, dp dt equals kp and then m minus p. So k and m will come straight out of that equation. But a is like your constant. So you're going to need some sort of initial value to be able to solve this. And so what you're going to do is you're going to use this, and you're going to have this equation on your test in my class. Now, as far as the AP exam goes, I have never come across anything that asks you to use this equation. What I have come across is problems that are set up similar to this, where you do have to solve and you have to use integration techniques like partial fractions, which is what you need for this to solve. And you get a problem that maybe has different variables. And so be on the lookout for that. And this, though, is simply something that in my class, you'll be given this problem on the test and you'll be asked to solve for A. And if you can do that, you'll be successful. On the AP exam, this is not, I've never come across this, and yet. I'll leave that possibility open. So let's apply. Let's see what it is. So last example here. In 1985 and 1987, the Michigan Department of Natural Resources airlifted 61 moose from Algonquin Park in Ontario to Marquette County in the Upper Peninsula. It was originally hoped that the population would reach the carrying capacity in about 25 years. That's neither here nor there. And the growth rate is given by this equation. Please pay attention to the quantity of zeros here and don't lose zeros. All right, let's answer a few questions. Question A, what is the limit as t approaches infinity of the population? This is asking for the carrying capacity. So carrying capacity. In other words, M. All right, this is M. 1,000. 1,000 moose. Question B, find the population when the population is growing the fastest. That's M over 2. 1,000, half of 1,000. That's going to be 500. So the population when the rate is the highest, halfway. You're halfway to your max, right? Find the particular solution. Okay, here's where we're going to have to remember. So let's remember the equation. It looks like this. You're going to use P equals M over 1 plus A e to the negative mkt. All right, let's start plugging things in. M is 1,000. 1 plus A I'm going to have to solve for. E to the negative. Okay, 1,000 times, this is K right up here, this point. So 1,000 will give me 0.3 T. Okay, I'm getting there. I'm making some progress. So how do I find A? Well, in order to find A, I'm going to need to know some sort of initial condition, okay? So to find that initial condition, I'm going to go back to the problem and I'm going to read through it. It said here that they began, when T is 0, they began with 61 moose. That's my initial condition. So the very first year when T was 0, T was 61. So now I'm going to use that and I'm going to solve for A. Here's what it's going to look like. 61 equals 1,000 over 1 plus A e to the negative 0.3 times 0. Okay, that's going to be e to the 0 is 1. I like it. That's going to be 1,000 over 1 plus A. Okay, that's not too bad. So now how do I solve this? Well, I'm going to multiply both sides by 1 plus A. So I get 61 times 1 plus A. I'm going to just multiply it on over. I'm going to keep it in its parentheses. And then I'm going to divide by 61. 1 plus A equals 1,000 divided by 61. Okay. And then subtract 1. 1,000 over 61 minus 1. Now I'm going to change this to 61 over 61. All right, 1,000 minus 61 is what? Like, oh gosh, mental math. 939. If I had a calculator, my notes from previous times say that this is approximately 15.393. That's fine. You can use a rounded answer. But then my last step is to make sure that I go back and plug it all back in. I'm going to go back up here. That's my A. We'll use 15.393. So here we go. Equals 1,000 all over 1 plus 15.393 e to the negative 0.3t. Boom. There's my equation. That's my solution, my particular solution to this. So essentially, if you know that formula, if you have it written down, you'll be provided with it. You need to know how to find A in my class. And then also for the AP exam, you need to know how to solve these differential equations. So that's going to be a second video that I'll post where we talk about solving this and where did the solution come from. But for now, you should be able to take this and answer most questions about logistic growth, including the carrying capacity, and knowing that we write it as the limit as t approaches infinity of the population. You should be able to tell me that the population grows the fastest when it's halfway to that carrying capacity. So these are questions that I want you to be able to answer, and now you should be good to go. And remember, if this all seems overwhelming, just keep at it, keep practicing. You can do this. You've got this.